Okay, so there's one other part of these colligative properties that we do need to take into account, and that is for specifically ionic solutes. So when we dissolve ionic things, right? Now, when ionic things are dissolved, they break apart into their ions. So what you have to do is actually multiply those colligative property equations or those concentrations by the number of particles or ions you have. And that is called the Van Hoff factor. So it's noted as a lowercase I. You'll see it on the equation sheet. Now, before we were talking about all of these molecular things or these covalent things, they don't break into ions. One particle is one particle. A complex carbohydrate looks the same whether you dissolve it or not. Ionic things do not, though. So if I'm using NaCl, for example, anytime I dissolve one molecule of NaCl, I actually get two particles. I get an Na plus and a Cl minus. So that actually doubles the effect on colligative properties. So since ionic compounds break apart, we have to multiply those colligative properties by the number of particles, by that Van Hoff factor. So NaCl's Van Hoff factor would be 2 because you get 2 particles. Okay? So what you'll notice is in each of my colligative property equations, I added this lowercase I. So you just got to multiply it by that. Okay, or you can think of it as multiplying the concentration by that, because we're actually like for NaCl doubling the concentration. Now, again, this only applies for ionic things. If it's covalent, NH3, this is not an ionic compound, it's just NH3. So its Van Hoff factor is 1, which is why we have ignored that little I up until now. Anytime you have an ionic compound, you have to figure out how many particles you're going to get. So CaCl2, when it dissolves, I get a calcium and 2 chloride ions. So that's actually 3 total ions. Whenever sodium carbonate dissolves, I get 2 sodiums and a carbonate ion. So that is 3. Now, remember, ionic things are only going to break into a positive thing and a negative thing. So you're only going to have positive and negative. That's why I wrote this one out over here. Positive thing is the sodium. The negative thing is the polyatomic ion. Polyatomic ions don't break up. Okay, so have your polyatomic ion sheet next to you. If you have more than 2 elements, one of them is a polyatomic ion. Okay, so I have sodium and carbonate. So this Van Hoff factor would also be 3. AlNO3, well, I get 3 nitrates and 1 aluminum. So that's actually a Van Hoff factor of 4. So the more particles you get in dissolving things, the more it will affect those colligative properties. So like aluminum nitrate would actually affect the boiling point or the freezing point times 4 times more than dissolving 1 particle of NH3. So those ionic compounds are really important, which is why we use salts on the road. We actually don't use NaCl, although it does, well, we use some, but it does have a Van Hoff factor of 2. We actually use things that have Van Hoff factors closer to 3 so that it can affect that freezing point a little bit more. Okay, so in example number 14, I say arrange the following solutions in order of the lowest to highest osmotic pressure. So it is based on concentration, but you really need to multiply by that Van Hoff factor. This would be times 2, so really like a 0.4 molarity. This one would be times 3, so really like a 0.45 molarity. This is a covalent compound, all nonmetals, right? So it's got a Van Hoff factor of 1, so it's still 0.25. This one has a Van Hoff factor of 3, so it'd be like 0.36. And this one has a Van Hoff factor of 2. This is a weak acid, H and C2H3O2. That's polyatomic ion right there. So it'd really be like 0.6. Ooh, this would probably be, I shouldn't have done this to you. This is a weak acid, so it doesn't really completely break up. This should be, I'm going to change this. This should be like actually less than 2. It should be closer to 1. I would not do this to you, so let's just like, I would take that out. I wouldn't give it to you. Okay, maybe if it was Chem 162, but it's not, so ignore that one. Okay, Van Hoff factors can be measured perfectly because like MgBr2 is not exactly 3, it's close to 3. So we're just going to use 3 for our instances. Okay, so in example number 15, it says, what is the predicted boiling and freezing points for a solution that contains 5.30 grams of Na2CO3? So this is ionic. You do need to determine the Van Hoff factor and incorporate it into your colligative properties calculation in 100 grams of water. These are the answers you should get. Your new boiling point should be 100.765, and your new freezing point should be negative 2.79. So go ahead and try that, try your work. Don't forget about the Van Hoff factor. Okay, and there's the work for you in case you wanted to see it. I just found the molality, plugged those in, multiplied them both by 3 because of the 3 particles in Na2CO3. I'm going to circle that. I is 3. Put that on here as well. sorry, I equals 3. Okay, so that's why I did that. And then I got my new melting and boiling point and freezing points going up and down.